Thanks for the introduction and invitations. Hi everyone, I'm Jiyuan Wang, a fourth-year PhD candidate at UCLA. Today I'll be presenting our work about differential testing for quantum software stacks. It was accepted for ASC 2021 and selected as 6th of the research highlight last year. So today's talk has two parts. First, I'd like to start with some background knowledge about quantum computing, which is necessary to understand our work, to help us better understand the second our work QDiff. So let's get started with some quantum computing background. I know everyone is here understand what is a quantum computer. It is hardware accelerators for certain computation tasks, like it just works like GPU or FPGAs, but only works on a very specific computing tasks. Oh, by the way, if you have questions, just raise and interrupt me at any moment. It will be fine. So I will briefly introduce some basic concepts, and then I will go a little deep to explore some hardware properties for QDiff. Okay, so let's start with qubit, the unstable state. The classical bit has two values, 0 and 1, and qubit is linear combinations of 0 and 1. For example, alpha 0 and beta 1. And the constraint of alpha and beta, alpha square plus beta square equals 1. So to read the information from the qubit, user should apply the operation called measurement. So if we apply the measurements on the alpha 0 and beta 1, we'll have alpha square probability to get 0 and beta square probability to get 1. The problem is how people build qubit on the real quantum hardware. So for classical bit, we construct 0 and 1 by electric current. So what about qubit? Qubit is usually a quantum system. It could be iron trap or superconductors, but it's a quantum system with two states. A low energy state called ground state will represent 0, and a relatively high energy state called excited state represent 1. So if we regard qubit as a football, we can represent 0 if we put football on the ground, and represent 1 if we put football on the desk. As you can imagine, the football on the desk is not stable, since it has a relatively high energies. It will gradually fall down to the ground by nature. So in quantum computer, it means the qubit has a short life. It will gradually decay from a high energy state, which is excited state, 1 state, to the low energy state, which is a ground state, 0 state. The average time for this decay happen is called T1 time. In other words, qubit will become unreliable after T1 time. So the quantum circuit execution time should less than T1, otherwise the results will become unreliable due to decay. Okay, any questions so far? Okay. So let's talk about the quantum gate and what nowadays quantum gate looks like. If we represent qubit in vectors, for example, we represent alpha 0 and plus beta 1 to be a 2 by 1 vector, alpha dot beta, then we can represent quantum gate as matrix, unitary matrix. For example, if the X gate transform alpha dot beta to beta dot alpha, so X gate is a 2 by 2 matrix listed as 0, 1, 1, and 0. So it's a unitary matrix. Every quantum gate can be represented in math as a unitary matrix. And only unitary matrix can issue the properties as the sum of coefficient square for each state should always equal 0. So there's other commonly used gate like Z gate, H gate, and C0 gate. If you write them in a metric form, they are all unitary matrix. Since all quantum gates can be represented as unitary matrix, we can transform a sequence of gates to another sequence of gates without alerting its outcome, as long as the multiplications of the matrix for gates in each sequence produce the same matrix. For example, H gate with X gate with H gate are equivalent to a Z. So what does quantum gates on nowadays quantum computer looks like? It has errors and a relatively very high error rate. And different kinds of quantum gate have different inherent error rate. For example, For public available IBM quantum computers, error rate of single qubit operations are in the order of 0.1%, while the error rate of 2-qubit gate operations like CNOT gate are in the order of 1%. A typical quantum program contains a significant number of 2-qubit gates. As you can imagine, if you want to map the logic qubit to the physical qubit, you need a lot of swap gates, which is consisted of the 3 CNOT gates, whose errors contribute the most to the overall error rate. So in other words, 2-qubit gates dominate the error rate. So if one quantum circuit has too many 2-qubit gates than its equivalent versions, then it may produce unreliable results. Okay, any questions so far? Okay, so now let's talk about the final quantum program or quantum circuit. Quantum circuit is just composed of the qubit, quantum gate, and the measurement in the end. For example, we have 2 qubits with 0 gate and 2 quantum gates, 1 H gate on the first qubit, and CNOT gate on both qubits, and measurement in the end. The result of the circuit will be either 0, 0 or 1, 1 with equal probabilities. So for most of the time, we will run and measure the circuit multiple times to get the distributions. The result is a distribution. Okay. To summarize, first, 2 quantum gate sequences are equivalent as long as they yield the same magical representations. These observations form the foundations of QDiff's equivalent program generations and differential testings. Second, developer needs to rapidly run and measure the results of the quantum circuit, and results will become a distribution. QDiff figure out a way to compare the distribution and ensure the correctness. Third and fourth are related with hardware noise. For example, the execution time of circuit should be less than T1. So that means the circuit depth should not be too large. Otherwise, the result is totally unreliable. And the circuit should only contain a small number of 2-qubit gates. Otherwise, the result will also become unreliable. So QDiff filtered out the worthless circuit based on these 2 rules. Okay, any questions so far? Okay, so let's start with our work, QDiff, the differential testing of quantum software stacks. This work is done with my advisor, me and Harry, and Qian Zhang, which is now an assistant professor at UC Riverside. The existing software applications are increasingly become computer intensive. So instead of using CPUs, there's a trend of heterogeneities. The heterogeneous computing is to port the computation expensive part to hardware accelerator for energy saving or for performance efficiencies. For example, GPUs and FPGAs that are originally built for computer graphs are now widely used for machine learning applications for speed up. Quantum computers as a new type of silicon alternatives is being prototyped. For example, today's IBM quantum computers. Is my screen sharing still works fine?
It works. Mm-hmm.
Okay. Does it work?
Yes, it works from my side. Zhidian, could you also confirm?
Yes, yes.
It doesn't work from my side.
Oh, really?
Yeah. Wait a second. I mean, sorry.
That's fine.
Okay, is it works fine? Can everyone
Yes.
see my screen right now? Okay. So I'll continue to introduce a little bit background. So different from GPUs and FPGAs that boost performance by parallelizations are called the processing elements. Quantum computers are able to reduce the algorithm complexities, leading to significant speedup. As an example for an unstructured search with global algorithm, quantum computer can reduce the computation effort from 2 to the power n to 2 to the power square n. Nowadays, quantum computing platforms are becoming actively researched and prototyped in industry. For example, Google is developing its own quantum programming language, Cirq, while another widely used language is PyQ developed by Rectis. With the development of the quantum hardware, IBM is now providing limited access to its quantum computers. All developers can run their quantum programs on IBM in IBM quantum language QuCS on its hardware. However, the real world is not perfect. There is bugs, errors in the QuCS, Cirq, and PyQ. We studied 76 bugs posted on Stack Overflow and GitHub regarding these 3 quantum software stacks. And besides the bugs in installations and interaction with other toys, we found errors happen in 3 parts. The first is language construct. For example, some gate APIs like QuCS crashes on signal gate. And then is some compiler settings. For example, QuCS may have some issues with some compiler optimizations options. And then it's the backend. It may crashes on the simulators, like PyQ crashes on PyQVM, which is quantum simulators. And it may also has issues with interactions with quantum hardware, like IBM's quantum hardware. Therefore, in order to exploit these bugs, testing method for quantum software stacks should target all 3 layers: the language part, the compiler options, and then the backends. However, the errors in quantum software stacks are hard to identify due to 3 challenges. First, it is hard to identify the right output of the quantum circuit. It is not easy to get the ground truth of the quantum circuit because the simulation of the quantum circuit can easily go out of the memory or running a huge amount of time. Second, even if we get the golden output, the ground truth, we still can determine if a divergent result is because of the bugs or because of the inherent probabilistic of natures. The inherent probabilistic nature of quantum computing makes error detection hard. For example, we find one post on Stack Overflow. The user saw the divergent results are due to a quantum nature until Cirq developers pointed out there was a potential errors in Cirq compilers. So we need to find a way to identify if this divergent result is because of the probabilistic natures or because of the potential bugs. Third, even if we identify the divergent result is not because of the probabilistic natures, it may still not be the bugs, because it may be because of the hardware noise. In other words, the quantum hardware noise can sometimes conceal the software bugs. To solve these challenges, first, QDiff generates quantum programs with the equivalent quantum gate transformations. They should yield the same results. So we build the ground truth by voltings. QDiff generates equivalent quantum programs by adapting 7 quantum gate transformation rules, and it can be easily extended by users. Second, QDiff adopts different testings with QuCS test-based distribution comparisons. We adopt QuCS statistic-based comparison to compare the program results with its equivalent versions and report divergence if QuCS statistic is larger than threshold. Thirdly, to make sure the bugs are coming from software but not coming from the no hardware noise. QDiff avoids the bad invocation of quantum simulator and hardware by analyzing two static features of quantum circuit. First is the circuit depth should less than a certain amount to make sure the execution of the quantum circuit is less than T1 time. And second, the 2 qubit number should less than a certain threshold. Any questions so far? Okay. The QDiff works as follows. With a state program and the target quantum software stocks, QDiff generates program equivalence with quantum gate transformations, and also explore the backends and the compiler settings. Next, QDiff avoids the unnecessary hardware and simulator invocations by analyzing static features of the quantum circuit. Then QDiff executes the circuit and compare the results with QuCS statistic. Finally, QDiff repeats the testing loop with a new program generated by mutation and reports divergent results if the equivalent version of the circuit if the result of equivalent versions report divergence. With QDiff, we find 4 software crashes in the Cirq and PyQ quantum simulators and 2 possible root causes for 29 divergent cases on IBM quantum hardware. The gate transformations are based on 2 observations. A quantum gate can be represented as a unitary matrix, and 2 quantum gate sequences are equivalent as long as they yield the same metric representations. QDiff adopts 7 commonly used rules in quantum compilations, and the metric representation doesn't change after these transformations. Users can easily extend their own rules as long as they can make sure the equivalence of these metric representations. Since all the transformations are equivalent, the result of this transformed circuit, which are probabilistic distribution, should also be equivalent, since we do not change the semantic of the circuit. QDiff also varies backend setting and compiler optimizations. For example, we can run circuit on different backends, from quantum simulators to state vector simulator and real quantum computers. And we'll also explore the compiler setting options, including customized optimizations and the other default compiler optimizations options. After QDiff generates a bunch of equivalent programs, we need to check the equivalency of their results. The result of quantum program is usually a distribution, since application developers usually repeat the measurement of quantum circuit for a certain amount. We adopt the QuCS test to compare the results and report divergence if QuCS statistic is larger than a user-defined threshold. The QuCS comparison works as follows. We first define the cumulative probability, that is, at all probabilities that are smaller or equal to x. And the QuCS statistic D is the max distance between 2 cumulative probabilities. We report divergence if D is larger than a user-defined threshold. Take the 2 following distribution as example. N1 and N2 are measurement distribution results for 2 qubit circuits. Users run and measure each circuit with total child number n equals to 1000 and get the following result in the first chat. We first calculate the cumulative probability in Y corner chat S1, S2. With S1 and S2, we calculate the QuCS statistic D as the max distance between them. It is clear D equals 0.06 in this example. QDiff will report divergence if D is larger than a user-given threshold, and the total child number n can be determined by the threshold T and the confidence level P given by the users. In our evaluation, we set P equals to 2/3, as it is a commonly used constant in statistic research, and we set T equals 0.1 to avoid the false positive. For the third challenges, QDiff avoids the bad invocations based on 2 observations. First, in quantum theory, a qubit can retain a correct state for only a limited amount of time, called T1 time. It is because qubit in high energy state usually is 1 state, will gradually lose its energies and fall back to the ground state. Usually it's 0 state. If the circuit has too many moments and the execution time is likely larger than T1 time, then the results of the circuit is unreliable due to a hardware limit. Second, 2-qubit gate dominates the error rate of the quantum circuit. If the circuit contains too many 2-qubit gates, then the result is also unreliable. For a quantum circuit, QDiff will first analyze the number of 2-qubit gates and the circuit depth. With the user-defined error rate threshold, the gate average execution time and 2-qubit gate error rate given by IBM website, QDiff will calculate the threshold for both circuit depth and 2-qubit gate number, and check if the invocation is necessary or not. We apply QDiff on 3 platforms, HiQ, Cirq, and QuCS. We generate 730 different quantum programs with semantic modifying mutations, and the program in turn produced 50,000 circuits with equivalent transformations. We reduce 66% unnecessary quantum hardware and simulated invocations and result in 2.9 times speedup. And we find 4 software crashes in simulation and 29 divergent cases in quantum hardware. So what QDiff find? Here's one example for bug in simulator backend. HiQ simulator fails into an illegal state after trying to run an empty circuit. Then the simulator will keep crashing even with non-empty circuit. QDiff detects these bugs by mutating an input quantum circuit to an empty circuit and executing it on both quantum simulator and state vector simulator. While the state vector simulator runs this empty circuit normally, the quantum simulator throws exceptions. Then QDiff generates an arbitrary non-empty programs. In the next few iterations, QDiff finds that these bugs because quantum simulator crashes while the state vector simulator does not. For 29 divergent circuit on quantum hardware, they're not bugs, but might due to the quantum circuit synthesis or bad compilations. Equivalent programs produce measurements that are flagged as divergence in terms of KS statistic. We speculate 2 possible root causes for 25 of them. 16 cases might because of the bad mapping from logic qubit to physical qubit, while 9 cases might because of the qubit defacings. So here's one example for one circuit given divergent results, which might due to the qubit defacings. 2 circuits are generated from different QuCS compiler optimization options, and the divergent circuit has no operations on qubit 4 for too long time, 18 moments in total. And thus, the defacing might happen and makes the measurement result of qubit 4 become unreliable. We need to keep qubit busy to make sure the qubit didn't lose its state. The QDiff detects that there is a significant difference between the result distribution of the divergent circuit and its equivalent circuit, and thus report the divergence. To summarize, we adopt differential testing to quantum software stacks. QDiff is effective in generating quantum program environments and avoids the bad invocation of quantum simulator and hardware. To end this talk, we want to share our findings when we're doing this project. My undergraduate major is physics, so that's why I push my advisor on these quantum topics. However, when we try to apply the software testing method on quantum software stacks, we find 1, we need deeper hardware knowledge to understand the root cause of the divergent cases we find when we're executing the equivalent programs on quantum computers. Right now, for some of the divergent cases, we don't know why they happen. We also ask experts from Google Quantum, but still there are some unknown reasons in hardware. Second, the initial purpose of QDiff is testing quantum software stacks. However, when executing on real quantum computer, we find the hardware noise conceals the software bugs, even with our 2 optimizations. So we need further effort to isolate the software stacks errors from the hardware noise. We release QDiff on GitHub. Feel free to check and let us know if you have any pros why these divergent cases happen. Thanks for listening. Any question?
Okay, thanks, Jiyuan, for the great talk. So if you have any questions, please unmute yourself or